This is our bovine kinetic data with substrate concentration in the first column and the activity V0 in the second column. So you should have seen how you can apply three transforms to this: the Lineweaver-Burke plot, the Haynes plot and the Hofstee-Edey plot, and each of these will have some advantages and disadvantages in terms of calculating Km and Vmax. An alternative way is to use a non-linear least squares curve fitting program such as Solver. So that's what I'm going to do now. So we need to put in some values for Km and Vmax. And the closer these are to the actual values, the better. So based on the three previous analyses, I'm going to go for a Km of 0.1 millimolar and a Vmax of 450. And then we need to estimate what V0 is. And we do that by using the Michaelis-Menten equation. So V0 is equal to Vmax. I'm going to copy this function down, so I'm going to put in $1. So it's Vmax multiplied by the substrate concentration, and I'll bracket that just in case, divided by, and again I'm going to bracket, Km plus the substrate concentration. And again I'll put $1 in there because I'm going to copy this function down. So here is an estimated value for V0 based on our estimated values of Km and Vmax of 0.1 millimolar and a Vmax of 450. So then we need to work out what is the difference between our estimated and V0. So this here is observed minus expected squared. So remember, for regression analysis we wanted to minimize the sum of squared deviations, and this is no different. So it's equal to, and it doesn't matter which way around these are because it's going to be squared anyway. And then we'll sum this. So we have a sum of squareds here, which we want to minimize. So the best fitting line to the data will be that minimizes the sum of squared deviations, just like it is for the regression line. And now we're going to use Solver to optimize the values of Km and Vmax to minimize this sum of squares. So we go data, Solver, so we should have added in Solver. We want to minimize the value which is in D11, which is our sum of squared deviations, by changing these two cells here for Km and Vmax. Sometimes it can be useful to put in constraints. So for example, we could say that the Km must be at least equal to or greater than 0. Vmax must be greater than 368, but less than, say, 100,000. But I'm just going to run solve. And we get solver has converged to the current solution. All constraints are satisfied. And you have a choice of either keeping the solver solution or restoring the original values. So we started off with a Km value of 0.1 millimolar. And solver has said that the value that minimises the sum of squared deviations, which should be the best fit, is really 0.077 millimolar. And the Vmax, rather than being 450, is 405. So I'll keep the solver solution. This looks nice. The great advantage of this technique is that we're not introducing artifacts by having to transform the data. The disadvantage is that it's not possible to get confidence limits around these two values for Km and Vmax. In order to do that, you have to use a dedicated package like nsfitter or sigma plot.